From the forest floor to high-tech factories, wood is shaped by some of the most powerful machines on Earth. In this video, we take you inside modern forestry and timber processing. Harvesters, presses, saws, and production lines working with precision, efficiency, and scale. This is how raw logs become engineered wood, firewood, and structural materials that build the world. The Valtra A93 Hi-Tech paired with the Nissula 325H harvester head represents a smart balance between compact design and professional forestry performance. Built for demanding woodland environments, this tractor-based harvester solution delivers the strength, control, and efficiency modern forestry operations rely on. At its core, the A93 is powered by a proven AGCO power engine, providing dependable torque and impressive fuel efficiency across long working days. Whether navigating thinning operations, selective harvesting, or processing small diameter timber, the engine maintains steady performance under load. The high-tech transmission enhances this capability with smooth power delivery and precise speed control, allowing the operator to maintain stability and accuracy throughout every harvesting cycle. Complementing the tractor is the Nissula 325H harvester head, engineered for light to medium-duty forestry work. High-speed feed rollers move timber efficiently, while the accurate measuring system ensures consistent log lengths. Delimbing knives are designed for clean, controlled cuts, reducing fiber damage and improving overall timber quality. The head's robust construction and balanced geometry contribute to reliable handling, even on uneven or challenging terrain. Seamless hydraulic integration between the tractor and harvester head results in responsive control and fluid operation. This synergy boosts productivity, reduces operator fatigue, and supports precise, confident harvesting. Together, the Valtra A93 Hi-Tech and Nissula 325H offer excellent maneuverability, low ground pressure, and lower operating costs. It's a versatile professional-grade solution for forestry contractors seeking efficiency, reliability, and performance in a compact mechanized system. The Narva S23 stroke harvester and firewood processor is a compact yet highly capable tool designed to meet the real-world demands of professional thinning, roadside timber processing, and small-scale firewood production. Built around mechanical simplicity and operational reliability, the S23 offers an efficient alternative to more complex harvesting systems, particularly in environments where durability and ease of use are critical. One of the defining strengths of the Narva S23 is its plug-and-work design philosophy. The unit installs quickly using the same hydraulic connections as the standard loading grapple, eliminating the need for additional hoses, electrical wiring, or external control systems. This streamlined setup dramatically reduces installation time while also minimizing potential failure points, making the S23 especially well-suited for harsh forestry conditions, remote work sites, and cold climates where electronic components can become a liability. At the heart of the S23 is a powerful guillotine cutting system, capable of processing timber with cutting diameters of up to 23 centimeters. This guillotine design delivers fast, decisive cuts with minimal energy loss, ensuring smooth operation during continuous harvesting cycles. The cutting action is clean and consistent, supporting efficient processing while reducing unnecessary strain on the carrier machine and hydraulic system. Timber feeding is handled through a robust stroke feeding mechanism that operates in controlled 50-centimeter movements. Rather than relying on complex roller systems, the stroke feed advances the stem in measured pulses, maintaining accuracy and reliability while keeping the mechanical structure simple. This design choice lowers maintenance requirements and improves long-term durability, especially during high-frequency use. All functions of the Narva S23 are controlled through a single hydraulic command, the opening and closing of the grapple. There are no additional switches, joysticks, or electronic interfaces required. Operators can work entirely through existing crane controls, allowing for intuitive operation and a significantly shorter learning curve. This simplicity enhances efficiency, particularly in operations where the same machine performs multiple tasks throughout the day. In addition to harvesting, the S23 seamlessly transitions into a firewood processor. By installing splitting wedges secured with just 3 bolts, the unit quickly shifts from timber cutting to firewood production with minimal downtime. Firewood length can be mechanically adjusted between 25 and 50 centimeters using limiting rods, providing consistent sizing without reliance on electronic measuring systems. The unit also features free rotation, enabling precise positioning during cutting, feeding, and splitting. This rotation system is fully hydraulic and mechanical, requiring no electrical power or additional control lines. The result is smooth, dependable movement that remains reliable even under demanding conditions. Overall, the Narva S23 stands out as a durable, low-maintenance, and cost-effective stroke harvester solution. By combining harvesting and firewood processing into a single robust attachment, it delivers dependable performance for professionals seeking simplicity, efficiency, and long-term reliability in forestry operations. The SpaltFix K650 is a mobile firewood production station built for speed, efficiency, and precision. Designed for seamless one-operator control, it delivers an impressive output of up to 60 cubic meters per hour, powered by a robust 16-ton splitting force. Adjustable log lengths from 5 to 65 centimeters ensure flexibility for any market demand, while optimized hydraulics reduce energy consumption by up to 20%. With all functions controlled effortlessly via joystick from the operator's cab, the K650 transforms firewood production into a fast, efficient, and highly streamlined operation. In the Moltal region of Carinthia, near the alpine town of Obervellach, this hydrogen phosphide Holz project showcases a highly advanced approach to forestry operations in one of the most demanding environments imaginable. Following severe storm events, large volumes of wind-thrown timber are left scattered across extremely steep mountain slopes, often in areas that are unsafe or completely inaccessible for conventional forestry machinery. In terrain like this, ground-based extraction is not only inefficient, but can pose serious safety and environmental risks. To overcome these challenges, HP Holz relies on downhill cable logging using the Synchrofox Skyline system. This technology makes it possible to extract storm-damaged timber in a controlled, predictable, and highly secure manner. Each log, or bundle of logs, is carefully lifted clear of the ground and transported along a precisely engineered cable line toward the valley floor. By minimizing ground contact, the system significantly reduces soil disturbance, limits erosion, and protects the remaining forest stand, an essential consideration in fragile alpine ecosystems where recovery can take decades. From a technical perspective, the Synchrofox system combines high payload capacity with exceptional stability, even across varying slope angles and complex terrain profiles. The Skyline is designed to maintain consistent line geometry, ensuring reliable guidance of the load throughout the extraction process. Synchronized control of pulling and braking forces allows for smooth, measured movement, preventing uncontrolled acceleration or swinging, and greatly improving operational safety for crews working both on the slope and at the landing area. Efficiency is another critical advantage. Despite the extreme terrain, the system supports continuous operation with minimal downtime. Well-planned line layouts and precise coordination enable high productivity, even under challenging weather and ground conditions. When paired with experienced operators and detailed operational planning, the Synchrofox system allows hydrogen phosphide Holz to recover valuable storm timber in an economically viable way. This operation in the Moltal region clearly demonstrates how modern cable logging technology provides a reliable, environmentally responsible, and technically robust solution for windthrow recovery in high mountain forestry, where safety, sustainability, and precision are paramount. Aboard the Daiwan Dolphin in New Zealand, the loading of logs unfolds as a precise bulk cargo operation supported entirely by the vessel's onboard cranes. Timber is delivered alongside and systematically lifted into the cargo holds, where a digger inside the hold distributes and stacks the logs to maximize space utilization and maintain proper weight balance. Each crane cycle is carefully coordinated with the hold operations to ensure smooth, continuous workflow and minimize idle time. The vessel's cargo handling systems prove well suited for high-volume log shipments, offering reliable lifting capacity and controlled placement. Throughout the operation, communication between crane operators and the digger driver remains critical to safety and efficiency. With stable conditions and well-executed procedures, the loading process proceeds without incident, demonstrating a straightforward, well-managed bulk log handling operation aboard the Daiwan Dolphin. The Stuvalar Machinery H2 Pro MSS 153F is a mobile 3-fraction screening machine built for high-volume processing of demolition wood, biomass, and compost. Featuring a 12 square meter adjustable vario upper deck, it delivers precise material separation while handling throughputs of up to 500 cubic meters per hour. Designed for modern job sites, it supports remote operation and is available in multiple size configurations, offering flexibility, efficiency, and reliable performance across a wide range of material processing applications. The Route automatic plywood pressing line represents the highest level of pressing technology in the modern plywood industry. Engineered to handle a wide range of wood species, veneer thicknesses, and resin systems, the system is designed to deliver consistent, high-quality panels under demanding industrial production conditions. By combining precision engineering, advanced automation, and long-term durability, Lathe provides a solution that meets both current production requirements and future manufacturing demands. At the heart of the system is a fully automated press line, where every stage of the process is precisely synchronized. Veneer layups are transferred accurately from the layup station into the press, supported by automated feeding, stack handling, and base plate management. This precise coordination ensures uniform pressure distribution across the entire panel surface, as well as exact thickness control throughout the pressing cycle. The result is stable panel geometry, reliable bonding performance, and minimal variation from panel to panel, even at high production speeds. The press line is designed with efficiency and ergonomics in mind. Advanced automation allows a single operator to control the entire system from a centralized interface. In high-capacity installations, one operator can supervise and manage two parallel press lines simultaneously, significantly reducing labor requirements. Automated stack forming, unloading, and base plate circulation eliminate much of the manual handling traditionally associated with plywood pressing, improving workplace safety while maintaining consistent production flow. Durability is a key element of Route's design philosophy. The pressing systems are built with heavy-duty frames and high-precision press platens capable of withstanding continuous operation at high press forces and elevated temperatures. Reliable hydraulic systems ensure smooth, repeatable motion, while integrated thickness monitoring and control systems maintain tight tolerances throughout long production runs. This level of control supports the production of premium-grade plywood with consistent mechanical and visual properties. With scalable configurations and seamless compatibility with modern upstream and downstream processes, the Route automatic plywood pressing line delivers exceptional productivity, reduced labor costs, and dependable quality. It stands as a benchmark solution for manufacturers seeking efficiency, precision, and long-term performance in plywood production. The story of West Fraser laminated veneer lumber, known as LVL, begins long before a finished beam ever arrives at a construction site. It starts in the forest and continues through one of the most highly integrated engineered wood manufacturing processes in the industry. At West Fraser's Sten LVL plant, every stage of production is designed with a clear purpose: to maximize material utilization, ensure consistent product quality, and deliver structural performance that meets the highest building standards. Each day, the process begins in the log yard, where logs arrive continuously, delivered by contracted log haulers from surrounding timber operations. As trucks pull in, material is unloaded using a high-capacity grapple machine or a Caterpillar 966 wheel loader. These machines play a critical role in maintaining flow, organizing incoming logs by size and species, and ensuring that production is never starved of raw material. Efficiency at this early stage sets the tone for everything that follows. From the log yard, logs are placed onto a transfer deck that feeds directly into the bucking station. This is where raw logs begin their transformation. The bucking station is an almost fully automated system combining computer-controlled movement with operator oversight. Advanced scanning technology evaluates each log, determining optimal cut lengths based on diameter, taper, and production demand. The system then executes precise cuts, ensuring maximum recovery while minimizing waste. Once bucked, logs move smoothly along conveyors toward the debarking process. Here, they enter a ring-style debarker equipped with 5 rotating arms, each fitted with hardened steel teeth. These arms strip away bark with controlled aggression, removing only what is necessary while protecting the valuable wood beneath. Proper debarking is essential, as even small amounts of residual bark can disrupt veneer peeling and reduce final product quality. After debarking, logs exit onto the slasher deck, named for the twin saws mounted above the deck. At this stage, logs are trimmed into standardized sections, typically 2 8-foot lengths. These precisely sized logs are now referred to as peelers, signaling that they are ready to enter the veneer production phase. Before peeling, each log passes through a scanning system that measures both length and diameter using a combination of photo eye timing and laser detection. This data allows the system to automatically assign each log to the correct peeler vat bin. From there, loaders transfer the logs into one of 10 massive conditioning vats. Inside these vats, logs are submerged in hot water for up to 12 hours. This conditioning process is critical. By softening the wood fibers, the hot soak allows the log to peel smoothly and consistently in the lathe. Without proper conditioning, veneer thickness would vary, surface quality would suffer, and material loss would increase. Typically, one loader manages vat filling, while a second loader feeds conditioned logs into the mill, keeping production steady and balanced. Conditioned logs then move to the Roundup infeed and are elevated via a jack ladder to the Roundup lathe. This machine removes any remaining bark that may have escaped earlier processes and ensures the log surface is perfectly prepared for peeling. From there, the log ascends another jack ladder and enters the spindleless lathe. The spindleless lathe is one of the most important machines in LVL manufacturing. Unlike traditional spindle lathes, it does not rely on fixed-end supports, allowing for higher recovery from smaller diameter logs. The log is driven through a series of powered rolls, while a continuous knife peels it into a long, unbroken veneer ribbon, approximately 1/8 of an inch thick. This ribbon forms the fundamental building block of laminated veneer lumber. As the veneer ribbon exits the lathe, it is guided onto one of 3 transport trays, each capable of handling veneer from logs up to 15 inches in diameter. These trays deliver the material to the clipper system, where the continuous ribbon is cut into standardized 4x8 foot sheets. During clipping, visible defects are removed and moisture levels are measured to support downstream quality control. The clipped veneer sheets move to the stacker, where they are sorted into bins based on moisture content. Moisture sorting is essential, as uniform drying behavior depends on consistent moisture levels. Veneer that does not meet full sheet specifications is diverted into random-sized pieces, which are collected and sold to plywood manufacturers. Any remaining unusable wood is conveyed to the chipper. The chipper reduces leftover wood into uniform chips, which are used in pulp production and other fiber-based applications. West Fraser takes pride in its near-total utilization of every log that enters the facility. Chips, fines, and residual material continue through the hog fuel system, where remaining wood waste is ground and prepared for energy generation. This material feeds the on-site energy plant, where hog fuel is burned to produce thermal energy used throughout the facility. Veneer dryers, heating systems, and other processes rely on this internally generated energy. Natural gas is available as a supplemental fuel source when required, ensuring uninterrupted operation. This closed-loop energy strategy significantly reduces waste and improves overall environmental efficiency. Dried veneer production begins at the dryer infeed, where veneer lifts are introduced based on 4 moisture categories: heavy sap, sap, light sap, and heartwood. The dryer operates at an average temperature of around 400 degrees Fahrenheit. Each veneer sheet spends approximately 3.5 minutes traveling from dryer infeed to outfeed, emerging with tightly controlled moisture content. Once dried, veneer sheets pass through density and moisture scanning systems. Density measurements provide insight into structural strength, while secondary moisture scans confirm final conditions. Based on this data, veneer is assigned either to plywood grades or directed into LVL production. Veneer suitable for plywood is sold to Alberta plywood plants, also operated by West Fraser, reinforcing the company's vertically integrated model. LVL production begins in the layup and press preparation area. Veneer lifts are loaded into automated feeders according to carefully engineered layup recipes. These recipes determine the number of layers, sheet orientation, and veneer placement, all based on the structural grade being produced. Every movement is controlled by computer systems to ensure precision and repeatability. As veneer sheets move down the line, they pass through a glue curtain, which applies adhesive evenly across all layers except the top face. The sheets then enter the layup zone, where they are overlapped and aligned into a continuous mat. By the time the veneer reaches the press, the layup consists of approximately 15 individual layers, working together as a single structural element. The LVL press itself is a continuous press system, meaning it operates without stopping during normal production. As the veneer mat enters the press, it passes through multiple high-powered microwave units. These units activate the adhesive and initiate bonding before the mat is compressed under hydraulic pressure of roughly 300 pounds per square inch. The result is a dense, dimensionally stable LVL billet with exceptional strength. The press produces approximately 3.6 million cubic meters of LVL annually. Once pressed, the continuous billet is cut into standard lengths ranging from 20 to 60 feet, depending on customer requirements. Finished billets are transferred using an overhead crane system capable of lifting loads of up to 20 tons. In the beam and header area, billets enter a gang saw fitted with multiple blades to achieve precise final widths. After sawing, boards undergo visual inspection, are trimmed if necessary, and then pass through a wax bath that seals exposed edges for added durability. Grade stamps are applied automatically, final inspections confirm quality, and boards are stacked, strapped, wrapped, and labeled with detailed product information. Finished LVL is then loaded for shipment, entering supply chains across Canada and the United States, where it becomes a critical structural component in residential, commercial, and industrial construction. This fully integrated process reflects more than 6 decades of innovation, efficiency, and commitment to quality at West Fraser's Sten LVL plant, transforming raw timber into high-performance engineered wood products that support modern building around the world. The Woodmiser HR115 resaw has officially entered production at a pallet manufacturing facility in Johor, Malaysia, marking the first installation of the HR115 equipped with Woodmiser's new Setworks control system. Designed for high-efficiency secondary breakdown, the HR115 delivers precise, repeatable cutting performance for pallet production and other high-volume applications. Capable of handling cants up to 400 millimeters in width, the machine provides consistent thickness accuracy across long production runs. In this installation, narrower cants are processed at feed speeds reaching up to 20 meters per minute, highlighting the HR115's impressive throughput potential. Even at these speeds, cut quality remains stable and controlled, demonstrating the reliability of the new Setworks system. The performance achieved here exceeds the pace typically suitable for newly trained operators, underscoring the HR115's role as a powerful, production-ready resaw solution. Custom milled log home manufacturing is a carefully controlled process that transforms raw timber into precision-engineered structural components. While log homes are often associated with traditional craftsmanship, The reality behind modern custom log construction is a blend of natural materials, advanced machining, and detailed engineering. Every log is treated as an individual structural element shaped to fit a specific position within a unique architectural design. The goal extends beyond basic structural strength to include tight fitment, long-term dimensional stability, energy efficiency, and a refined finished appearance. The process begins with log selection and preparation. Raw logs are sourced based on species, growth characteristics, and suitability for structural use. Each log is inspected for diameter consistency, straightness, moisture content, and natural features such as knots, checks, and grain orientation. These characteristics influence how the log will behave over time and how it will be used within the structure. Only logs that meet strict criteria move forward into production. Once approved, a log is transported to the milling area and positioned onto a heavy-duty milling bed. The log is carefully aligned and securely clamped to prevent movement during machining. Maintaining this stability is essential, as even minor shifts can affect dimensional accuracy. Computer-guided measurement systems then reference detailed construction drawings to determine the exact length, exterior profile, and locations for all joints, penetrations, and connection points. These digital references ensure that every cut corresponds precisely to the overall building plan. The first machining operation typically involves cutting the log to its final length. Precision saws create clean, square end faces that will later form tight joints at corners or mid-wall connections. Trimming operations follow, removing excess material and refining the outer surface of the log. Depending on the architectural design, the log may retain a fully round profile, be milled into a D shape, or feature a custom contour. These profiles are not purely aesthetic. They influence how logs stack, how well they seal against one another, and how effectively the wall resists air and moisture infiltration. Drilling is the next critical phase. Holes are precisely bored to accommodate fastening systems, alignment pins, electrical chases, and service penetrations. These features must align perfectly across multiple logs once the structure is assembled on site. Drilling with millimeter-level accuracy ensures that walls stack true and that logs settle uniformly over time. Controlled settling is an essential consideration in log construction, allowing the structure to adjust naturally to changes in moisture and temperature without compromising wall integrity or creating gaps. Notching represents one of the most technically demanding stages of the process. Each notch is machined to match the geometry of intersecting logs at corners, mid-wall junctions, and load-bearing intersections. Saddle notches, dovetail joints, and proprietary interlocking profiles are cut to ensure maximum surface contact and efficient load transfer. Properly executed notches provide resistance to wind loads, lateral movement, and long-term settling. The precision achieved at this stage directly affects both the speed of on-site assembly and the structural performance of the completed home. As production continues, each log is customized according to its role in the structure. Some logs are standard wall components, while others serve specialized functions. In this workflow, a second log is prepared to integrate with a custom timber truss system. Truss-supporting logs require additional machining to create bearing surfaces, angled interfaces, and mounting points for structural hardware. These elements must align exactly with engineered truss components, so roof loads are transferred efficiently and evenly into the log walls below. Throughout the entire manufacturing process, quality control is continuous. Measurements are checked against digital plans, surface finishes are inspected for consistency, and joint tolerances are verified. Any deviation is corrected immediately, ensuring that every log meets strict production standards before leaving the facility. This attention to detail minimizes the need for on-site adjustments and reduces material waste during construction. Once completed, each log is uniquely identified, labeled, and sequenced according to the assembly plan. The finished log package represents a complete structural system, where every component has a defined position within the building. When delivered to the construction site, the logs fit together like a three-dimensional puzzle. This level of precision dramatically shortens build time while ensuring accuracy, energy efficiency, and architectural consistency. Custom-milled log home manufacturing combines the authenticity of traditional timber construction with the precision of modern machining. By carefully cutting, trimming, drilling, and notching each log, manufacturers create homes that celebrate the natural beauty of wood while meeting contemporary expectations for durability, performance, and construction efficiency, PolyPress is a fully automated, curved beam press developed for the precise and efficient production of single, curved glulam beams. Engineered specifically for batch size 1 manufacturing, it enables a direct digital workflow from design to finished component, allowing complex, curved timber elements to be produced without manual handling. This capability transforms architecturally demanding curved structures from a technical challenge into an economically viable solution. The system features automatic loading and unloading, combined with CNC-controlled positioning that ensures exact geometric setup for every individual beam. Both straight and curved press beds are supported, offering maximum flexibility in beam design and production. Forming and pressing shoes are positioned by motorized drives, adapting automatically to each beam's unique curvature, while short-stroke hydraulic cylinders apply uniform, controlled pressure across the full lamination length. PolyPress operates with fully programmable pressing cycles, including automated side pressure control and continuous pressure monitoring with real-time adjustment. This high level of automation allows the use of fast-curing adhesive systems, significantly reducing pressing times and increasing throughput. Despite its advanced functionality, the entire process can be efficiently supervised by a single operator. With low energy consumption, exceptional repeatability, and a modular expandable design, PolyPress establishes a new standard for precision, efficiency, and flexibility in curved glulam beam manufacturing. The ALS 4.0 linear saw represents the latest evolution in automated linear cutting technology from Alpine equipment. Developed through more than a decade of direct customer feedback and real-world production experience, the ALS 4.0 is engineered to meet the changing demands of modern building component manufacturing. Performance, safety, and efficiency are embedded into every aspect of its design, making it a powerful solution for today's high-throughput production environments. A key feature of the ALS 4.0 is its fully enclosed, safety-first architecture. All cutting operations take place inside a rigid main cabinet, significantly reducing exposure to moving components and virtually eliminating the risk of accidental contact with the saw blade. This enclosed design also contains sawdust and offcuts, creating a cleaner, quieter, and healthier workspace while improving overall housekeeping on the production floor. The ALS 4.0 is available in 4 base configurations, including both standard and high-speed models, with optional beveling capabilities to accommodate a wide range of cutting applications. This modular approach allows manufacturers to tailor the system precisely to their production requirements, whether the focus is on volume, precision, or specialized cuts. Material handling is optimized for continuous, uninterrupted flow. The standard model processes lumber at speeds of up to 102 inches per second, while the high-speed version reaches an impressive 160 inches per second. Cutting speeds are automatically adjusted in real time to maintain consistent throughput and optimal cut quality. An integrated in-feed inkjet printer marks boards before cutting, eliminating manual labeling while improving traceability and downstream identification. Flexible in-feed and out-feed conveyor configurations support lumber lengths ranging from 4 feet to well over 20 feet. This flexibility enables true one-operator operation, even in high-capacity production settings. Advanced servo motors, a redesigned saw head, and precision blade systems ensure fast setup times and cutting accuracy of 1/16 of an inch or better. When combined with intelligent optimization software, remote diagnostics, and detailed production reporting, the ALS 4.0 delivers exceptional material efficiency and operational transparency. Together, these capabilities position the ALS 4.0 as a new benchmark in productivity, safety, and precision for automated linear saw systems in modern manufacturing. This project demonstrates the complete construction of a frame garage workshop built entirely by a single builder. It highlights how thoughtful engineering decisions, efficient sequencing, and hands-on problem solving can replace additional labor when a project is carefully planned from the start. The structure follows classic frame construction principles, optimized for durability, functionality, and ease of assembly, proving that complex building projects can be successfully completed by one person without compromising structural integrity. The process begins with careful site preparation and foundation work. A stable, level base is essential, as every part of the structure depends on it. The site is graded and compacted to prevent settlement, and a layer of gravel is installed to promote drainage and load distribution. On top of this, a reinforced concrete slab or pier system is constructed, designed to support the building's weight and resist long-term movement. Accurate layout, squaring, and elevation checks are critical at this stage, because even small errors in the foundation will multiply as framing progresses. Once the foundation is complete, wall framing begins using dimensional lumber, typically kiln-dried timber chosen for its strength, straightness, and consistency. Stud spacing is carefully calculated to meet structural codes while also allowing space for insulation, interior finishes, and future electrical work. Each wall section is assembled flat on the ground, a method that allows a single builder to work safely and maintain precise measurements. Once framed, walls are raised into position one at a time and temporarily braced, ensuring stability while the structure takes shape. Top and bottom plates are aligned and securely fastened, tying the wall sections together into a rigid structural loop. Corners and intersections are reinforced to handle lateral loads, while door and window openings are framed with appropriate headers to support weight from above. Throughout this phase, constant checking for plumb, level, and square ensures the building remains true as it rises. Roof construction is approached with simplicity and strength as guiding principles. Prefabricated rafters or site-built trusses are installed to provide adequate load capacity for wind, snow, and roofing materials. The roof pitch is selected to balance weather performance with material efficiency, allowing rain and snow to shed while minimizing complexity. Once installed, roof sheathing is applied, locking the entire frame together and preventing racking under load. With the main structure secured, exterior sheathing is installed using oriented strand board or plywood. This step adds significant rigidity and prepares the building for weather protection. A moisture barrier is then applied to shield the frame from rain and wind infiltration, protecting the structure during construction and throughout its service life. Exterior cladding follows, selected for durability, low maintenance, and long-term performance, transforming the exposed frame into a weather-tight enclosure. Doors and windows are installed next, with special attention given to the wide garage door opening required for workshop use. Reinforced framing ensures the opening can withstand repeated use and structural loads. Proper alignment, flashing, and sealing prevent air and water leaks, improving both durability and energy efficiency. Finally, the workshop interior is prepared for practical use. Electrical conduits, lighting layouts, and power outlets are planned to support tools, machinery, and efficient workflow. Lighting is positioned to eliminate shadows, and power access is distributed to reduce the need for extension cords and temporary solutions. The completed garage workshop stands as a fully functional structure built entirely by one person. It demonstrates that with careful planning, sound construction principles, and disciplined execution, solo builders can achieve professional-level results while maintaining safety, efficiency, and structural reliability. This advanced 8-foot wood veneer rotary peeling lathe stands at the heart of modern plywood production, serving as one of the most critical machines in the entire manufacturing line. Designed for high productivity, precision, and maximum material efficiency, the system is engineered for continuous industrial operation where consistency and yield are essential. Its CNC-controlled spindleless peeling technology represents a significant evolution from traditional lathe designs. Before peeling begins, raw logs undergo debarking to remove bark, dirt, and other impurities that could damage equipment or compromise veneer quality. Once prepared, the logs are transferred directly into the 8-foot spindleless veneer lathe. Instead of relying on conventional end spindles, the system uses synchronized drive rollers to securely grip and rotate the log along its length. This spindleless configuration allows the machine to process logs more completely, dramatically reducing core size and maximizing usable veneer recovery. As the log rotates, a high-precision peeling knife advances steadily toward the center, shaving the log into a continuous veneer ribbon with uniform thickness across the full 8-foot width. CNC control governs every aspect of this process, including knife position, feed rate, and cutting depth. This level of automation ensures stable operation and consistent veneer thickness, even when processing hardwood species or logs with varying diameters and internal characteristics. Once peeled, the continuous veneer ribbon flows seamlessly into the integrated clipping system. Here, the ribbon is trimmed into standardized veneer sheets with precise dimensions. Automated clipping improves accuracy, reduces waste, and eliminates the need for manual handling between peeling and clipping. The resulting veneer sheets are immediately ready for drying and subsequent layup, supporting an uninterrupted production flow. Built with heavy-duty components and designed for high-speed operation, the lathe performs reliably under demanding factory conditions. Its robust construction supports round-the-clock production, making it well-suited for large-capacity plywood mills focused on efficiency and output. By supporting the complete A to Z plywood manufacturing workflow, from debarked log to ready-to-dry veneer, this 8-foot peeling and clipping lathe forms a critical foundation of modern plywood production. With advanced automation, high recovery rates, and consistent veneer quality, it delivers the performance and reliability required for efficient, industrial-scale plywood manufacturing.